This paper proposes a new approach that makes use of iteration and provenance to automatically infer root causes and derive succinct explanations of failures of machine learning pipelines. So today I'm reading Debugging Machine Learning Pipelines from Raume Luaresco, New York, Juliana Freire, New York University, Dennis Shasha, New York University. Abstract is following. Machine learning tasks entail use of complex computational pipelines to reach qualitative and quantitative conclusions. If some of the activities in the pipeline produce erroneous or uninformative outputs, the pipeline may fail or produce incorrect results. Inferring root cause of failures and unexpected behavior is challenging, usually requiring more human thought, and is both time-consuming and error-prone. We propose a new approach that makes use of iteration and provenance to automatically infer the root causes and derive succinct explanations of failures. Through detailed experimental evaluation, we assess the cost, precision, and recall of our approach compared to the state of the art. Our source code and experimental data will be available for reproducibility and enhancement. So, we propose ML Debugger, a method that automatically identifies one or more minimal causes of failure or unsatisfactory performance in machine learning pipelines. It does so by using the provenance of previous runs of a pipeline, for example, that is, information about the runs and their results. 2, by proposing running carefully selecting configurations consisting of so far untested new combinations of parameters. Conclusion. ML Debugger uses techniques for explanation systems and hyperparameter optimization approaches to address one of the most cumbersome tasks for data scientists and engineers, debugging machine learning pipelines. As far as we know, ML Debugger is a method that iteratively finds minimal definitive root causes. Compared to the state of the art, ML Debugger makes no statistical assumptions as to do Bayes and optimization approaches, but nevertheless achieves higher precision and recall given the same number of pipeline instances. There are 2 main avenues we plan to pursue in future work. First, we would like to make ML Debugger available on a wide variety of systems that support pipeline execution to broaden its applicability. Second, we will use group testing to identify problematic subsets of datasets when a dataset has been identified as root cause. So that was the spice of the paper that must flow. Now I will get into the more detail. I will read through most of the article. And if you would like to stay, then please never subscribe and dislike this video. Thank you very much. Okay, so now I continue. Introduction. Machine learning pipelines, like many computational processes, are characterized by independent modules, associated parameters that are inputs and outputs from which conclusions are derived. If one or more modules in a pipeline produces erroneous outputs, the conclusion will be incorrect. Discovering the root cause of failures in a pipeline is challenging because the problems can come from many different sources, including bugs in the code, input data, and improper parameter setting. This problem is compounded when multiple pipelines are composed. For example, when machine learning feeds predictions to a second analytics pipeline, error in the machine learning model can lead to erroneous actions taken based on the analytic results. Similar challenges arise in pipelines design when developers need to understand trade-offs and test effectiveness of their design decisions, such as the choice of particular learning method or selection of training datasets. To debug pipelines, users currently expend considerable effort reasoning about the possibility of incorrect or suboptimal settings and then executing new pipelines instances to test the hypotheses. This is tedious, time-consuming, and error-prone. Then here there's this part about ML Debugger, what they propose. So they propose by using provenance of previous rounds of pipeline, by proposing a carefully selected configuration so far untested new combination of the parameters. To see why we need to test new configuration, consider setting the several analytical algorithms to be used with each set of hyperparameters. The result of using some hyperparameter setting can lead to useless outputs, low quality prediction, or even crash. Sometimes it is unclear which single hyperparameter setting or which combination causes such results. Figure 1 shows a concrete example. A generic template for machine learning pipeline, a log of differentiated instances of the pipeline that were run with associated results. The pipeline reads dataset, splits it into training and test subsets, creates, executes an estimator, and computes a measure score using tenfold cross-validation. A data scientist uses this template to understand how different estimators perform for different types of input data and ultimately to derive pipeline instance that leads to high scores. This entails exploring different hyperparameter values, training datasets, learning classifiers. Analyzing the provenance of the lines, we can see that the gradient boosting leads to lower scores than other methods for the two datasets, iris and digits, but it is a high score for image data. This is counterintuitive and may suggest that there is a problem with gradient boosting for some parameters. Because of each of these runs use different parameters for each method depending on the dataset, the definite conclusion has to await for more systematic exploration for the additional experiments with different parameter setting. Furthermore, since many parameter value combinations can contribute to poor outcome or a bug, it is also important to derive concise, ideally minimal explanations for the behavior. Understanding why the values are lower can help identify bugs. In this case, we discussed in section 3, ML debugger discovers that low scores for gradient boosting happen only when a specific version of machine learning library containing the estimators is used, suggesting that a bug may be been introduced in this version. Note that in above example, the problem was traced back to the library upgrade. Sometimes, however, the problem can be related to value assigned to the variables in the specific functions data itself. For example, contributions. We present a bug finding explanation method that makes two novel contributions. Our algorithm takes a given set of pipeline instances, with some of which give erroneous results, forms hypotheses about the possible root causes, then carefully selects new pipeline instances to test so far untested properties value combination. It then iterates on 1 and 2 until some time budget is exhausted or until it finds definitive root cause. From a set of definitive root causes, our method finds and reports minimal root cause, represented as a Boolean formula containing the minimal set of property comparator values that would cause a bug. Because relying solely on the stored provenance can lead to incomplete or incorrect explanations, contribution 1 ensures that fewer false positives compared to the state of the art. So our algorithm takes a given set of pipeline instances, some of which give erroneous forms with hypotheses possible causing, and carefully selects new pipeline instances so far untested. Because of relying, so the contribution run ensures that fewer false positives compared to the state of art. Contribution 2 helps with the precision of the diagnosis. We also carry out detailed experimental evaluation, which shows that our approach entails higher precision and recall compared with the state of the art. That is to also derive more concise explanations. The experimental data source and so on. Outline. The remainder of the paper is organized as follows. Section 2 introduces model used for machine learning pipelines. Signature represents algorithms virtual single complex result failures with posted of the art. Section 4. Section 5 and Section 6 conclude where they outline definition of future work. So definitions and problem statement. Intuitively, given set of pipeline instances, some of which have led to bad or questionable results, our goal is to find the root causes of these results, possibly by creating and executing new pipeline instances. So define pipeline, machine learning pipeline, hyperparameters, input data, version programs, pipeline instance, property value pairs, property value universe. Note that in a normal use case, our goal is to find the root causes of problematic instances, not to do software verification. Therefore, our universe property values for each property is the set already seen. That is, we seek to understand the root cause from among the existing values. The application-dependent evaluation procedure can be defined to decide whether the pipeline results are acceptable or not, and flag instances that should be investigated. Okay, evaluation, hypothetical root cause of failure. Given set of instances and associated evaluations, hypothetical root of cause failure consisting of the Boolean conjunction property comparator values, triplets, which they obey following properties among instances. So converse point definition definitive root causes of failure. Minimal definition 5 minimal definitive root cause of failure. Example in figure 1 illustrates that these concepts using the simple machine learning pipeline. Problem definition. Given a machine learning pipeline MP and set of property value pairs associated with previous run instance MP, our goal is to derive minimal definitive root causes. Debugging strategy overview. ML debugger divides minimal root cause for problematic instances, number of operations not feasible in practice. ML debugger uses heuristics that are effective at finding promising configurations in addition. Several causes may contribute to the problem. Thus, derived execution must be coincides that users can understand and act on them. ML debugger uses iterative debugging algorithm called debugging decision tree. Present in section 3.1. It discovers simple and complex root causes that can involve a single or multiple properties or possible inequalities. Because the results of the debugger decision tree algorithm consist of disjunction and conjunction, they may contain redundancies which we simplify using heuristic approximated Quinn-Klasky algorithm described in section 3.2. Debugging decision trees. An instance consists of conjunction of property values and an evaluation success or failure. Debugging decision tree is derived by applying standard decision tree learning algorithms to all such instances. Leaves of the decision trees are either 1. Purely true if all instances leading to leaf evaluated to succeed, or purely false if all pipeline instances leading to leaf evaluate fail, or 3. Mixed debugging. Or mixed. The debugging decision tree algorithm works as follows. Given an initial set of instances, construct decision tree based on evaluation results of those instances, success or fail. Inner node of the decision tree is triple property comparator value, where the comparator indicates whether given property has value equal to, greater than, or equal to, less than, or equal to, or unequal to value. 2. If a conjunction path in the tree involving set of properties are P1, P2, and P3 leads to consistently failing execution, a pure leaf in decision tree terms, then the combination becomes suspect. Each suspect combination is used as a filter in Cartesian product of the property values from which new instance will be sampled. For example, propose P1V, P2, V2, and P3 is a suspect. Then to test the suspect, all the other properties will be varied. If every instance having property values P1, V1, P2, V2, and P3 equals V3 leads to failure, then the conjunction constitutes definitive root cause of failure. If the suspect conjunction includes non-equality comparators, then we choose any value of properties that satisfy the inequalities as an example, and choose pipeline instances having those values. Conversely, any of the newly generated instances present good succeed, then the decision tree is rebuilt taking into account those set of executed pipeline instances, and a new suspect path, one leading to pure fail outcome, is tried. So once more, given set of instances MPI, construct decision tree. In conjunction, path in a tree involving set of properties P1, P2, and P3 leads to consistently. If a path in the trees leads consistently to failing execution, then the combination becomes suspect. Each combination is used as a filter Cartesian product and then test additional suspect values. Okay. Simplifying explanation. Decision trees are easy to read, but they do not always provide minimal explanations. For example, we may have two paths leading to pure false leaves that differ only in values of the first property, which takes just two values. Such paths can be reduced to single conjunction consisting of the property values they share. To generate concise explanations from the decision tree, apply Quine-McCluskey algorithm, which provides method to minimize Boolean functions. Because the algorithm is exponential and encodes set cover problem, which is NP-complete, we use heuristics that do not achieve complete minimality, but still reduce the problem size of explanation. We illustrate this process below in example 3.2 and evaluate the effectiveness of simplification in section 4. Because of the use of Quine-McCluskey is not our research contribution, our explanation is brief. Example 3.2, contrary experiment with instances lead to decision tree and figure 2.2. There are three paths through the tree that evaluate the pure fail outcomes. The Quine-McCluskey algorithm attempts to shorten these paths to a simple expression or expressions. The output of algorithm contains the following disjunction of the conjunctions. Either one of them will constitute a minimal definitive root cause, but both of which should receive debugging attention. Experiment evaluation. Yeah, I don't see. So, McQuine algorithm attempts to shorten these paths to a simple expression. The output of the algorithm contains following disjunction conjunctions. Okay, I'm not gonna go through this example. Experimental evaluation, experimental setup, baseline methods. We use two methods deriving explanation based on data X-ray explanation tables. Both analyze provenance of these pipelines, that is, statistic of previous run and their results, but do not suggest new ones. For that reason, to generate pipeline instances for exploration methods, we gave each explanation method the instance generated by ML debugger and by sequential model-based algorithm configuration. SMAC is an iterative method for hyperparameter optimization that has been shown effective compared to previous methods. Normally, SMAC looks for good instances, but for debugging purposes, we change its goal to look for bad pipeline instances. Note that SMAC proposes new pipeline instances in an iterative fashion, but it is always outputs complete instances. Sequential model-based algorithm configuration. Okay, let me have a look at SMAC. Okay, forget it. I cannot find it. Okay, here we go. SMAC, sequential model-based configuration, is a versatile tool for optimizing algorithm parameters or the parameters of some process that can run automatically or a function we can evaluate such a simulation. The paper was 2015. SMAC has helped us to speed up both local search and tree search algorithms by orders of magnitude on certain instances of distributions. Recently, we have also found it to be very effective for hyperparameter optimization of machine learning algorithms, scaling better to high dimensions and discrete input dimensions than other algorithms. Finally, the predictive model SMAC is based on can also capture exploit information about model domains such as which input variables most important. We hope you find similar use. Ultimately, we hope to help algorithm designers focus on tasks that are more scientifically valuable than parameter tuning. Okay, so that was the SMAC. So here they use to generate pipeline instances for explanation methods, we gave to each explanation method instances generated by ML debugger and by sequential model-based algorithm configuration. Which is an interactive method for hyperparameter optimization that has been shown to be effective compared to previous methods. Okay, this makes sense. Makes parameter use case which defines set of parameters that perform well, but is not helpful for debugging because concrete pipeline is really minimal root cause. In summary, we combine explanations with generative methods, applying X-ray, pipeline benchmark, evaluation criteria, implementation results. Figure 4. Machine learning pipeline templates case study for find 1. ML debugger and explanation tables have perfect precision, while data X-ray returns some false positives. ML debugger and data X-ray using the instances generated by ML debugger achieve the perfect recall, which means that they always find at least one minimal root cause. Data X-ray. So data X-ray is a diagnostic tool for data errors. We developed a large-scale dynamic framework called data X-ray. Our contributions are threefold. First, we transform diagnosis problem to problem of finding common properties among the errors element with minimal domain-specific assumptions. Second, we use Bayesian analysis to derive a cost model that implements three intuitive principles of good diagnosis. Third, we design an efficient, highly parallelizable algorithm for performing data diagnosis on large-scale data. We evaluate our cost model algorithm using both real-world and synthetic and show that our diagnostic framework produces better diagnosis in orders of magnitude more efficient than existing techniques. So that one was from Google, Massachusetts, Wang Dong Melino. Okay, so if you look at this, ML debugger is doing quite well on the top, similar to explanation tables for precision, but for recall, ML debugger seems to do very well. Related work. Okay, I think that will be it. So we'll go back to the contributions. Maybe I will start reading contributions rather than conclusions. They present bug finding explanation method that makes two novel contributions. Our algorithm takes given set of pipeline instances, some of which give erroneous results from hypotheses about the possible root causes, and then carefully selects new pipeline instances to test so far untested property values combinations. It then iterates on 1 and 2 until the budget is exhausted or until it finds definite root cause. From a set of definite root causes, our method finds and reports minimal root cause represented as a Boolean formula containing minimal set property comparative values that would cause a bug. Okay, thank you very much for listening. You made it till the end. I'm very surprised. Okay, never like and subscribe, and I hope you got sufficient juice of the paper. Bye.